Hello guys. Today now we're gonna consider Fermat's theorem and Euler's theorem. So Fermat's theorem and Euler's theorem are very fun topics. If you haven't studied, please go back to your lecture slides and review them. All the definitions and examples are given. Now I'm not gonna explain the theorem itself. I'm just gonna show how we use Fermat's theorem and Euler's theorem to solve problems. Okay, now let's consider this problem. Show that 2 to the power of 6 to the power of 2 minus 1 is divisible by 7 using Fermat's theorem. Right? So remember, Fermat's theorem says that a to the power of p minus 1 gives you remainder 1 when divided by p. And in this case, this p is prime, right? And a not divisible by p. Okay? So in our case, we're dividing by 7. So 7 is prime. Okay? Now we can use Fermat's theorem, right? My a will be, in this case, 2. So and 2 is not divisible by 7. So I can use Fermat's theorem. Now, the first of all, okay, by Fermat, what I have is 2 to the power of 7 minus 1, right? P minus 1 gives me remainder 1 mod 7. So which is basically 2 to the power of 6, right? Gives me remainder 1 when divided by 7. Now I need to have this expression, right, basically. Now let's consider this part first. 2 to the power of 6 to the power of 2. So remember that 2 to the power of 6 to the power of 2 is 6 squared is 36, right? So this is basically 2 to the power of 36. Well, 2 to the power of 36 also can be written as 2 to the power of 6 outside power of 6. Okay? So I have this expression. Now what I can do is, since I know that 6 is positive integer, right? I can raise both sides, okay, of this expression to the 6th power, right? So I can say is raise this to the 6 and 1 to the 6. So if I raise 1 to the power of 6 is still 1. And this one will give me what I need, right? 2 to the power of 36. So 2 to the power of 36 gives me 1 mod 7. Okay? Now what I can do is subtract 1 from each side of this expression, right? If I subtract 1, I will have 2 to the power of 36 minus 1. Over here, 1 minus 1 is 0 mod 7. Right? And I know that 2 to the power of 36 is basically my expression what I needed. So therefore, when I divide this number by 7, remainder is 0, right? So this is saying remainder equal to 0. Therefore, this expression, right, 2 to the power of is divisible by 7. Is divisible by 7. So that's it basically. Okay, how you apply Fermat's theorem. Now this problem is kind of easy. Now let's consider a little bit more difficult one. Okay, so show that for any positive or non-negative integer n, this expression that 3 to the power of 12n minus 2 to the power of 12n is divisible by 35. Now, if I want to use Fermat's theorem in this case, right, I cannot use it directly because I cannot divide by 35 since 35, okay, this one not prime, right? Not a prime number. But what I can use instead is factors of 35, right? So 35, remember, is 5 times 7. and each one of them are prime, right? Primes. Therefore, I can separately consider by dividing by 5 and dividing by 7. And I can consider obviously this expression as a whole, right? But what I want to do is make it simpler, right? So consider each one separately. 3 separately and 2 separately. And then at the end, we're going to subtract them from each other. So first, okay, consider by, divide by 7. So if I divide by 7, by Fermat's theorem, 7 is prime, right? 3 and 2 and 3 are not divisible by 7. Okay, so basically I will have 3 to the power of 7 minus 1 as over here, right? Similar to the previous one. 7 minus 1 is 6 to the power of 3 to the power of 6 gives me remainder 1 mod 7. And by the same logic, 2 to the power of 6 gives me remainder 1 mod 7. Okay, right? But I need 12, right? So what I can do is, and since I also know that n is positive, right, non-negative integer, right? I can raise this to the power of 2n, and this one also, and this 2 to the power of 6 to the power of 2n, and therefore this will give me 3 to the power of 12n gives me remainder 1 mod 7, and 2 to the power of 12n gives me 1 mod 7. Okay, so next is divide by 5 by the same logic. Okay. Divide by 5. Now we will have 3 to the power of, remember, p minus 1, right? 3 to the power of 4 gives me remainder 1 mod 5, and 2 to the power of 4 gives me 1 mod 5 as well, right? But remember, my expression is 3 to the power of 12n and 2 to the power of 12n, right? So to get 12n, what I can do is I can raise this to the power of 3n, right? And this one as well. So if I raise it to the power of 3n, right, this will be 3 to the power of 12n gives me 1, right? And 1 to the power of 3n is also 1 mod 5. And by the same logic, 2 to the power of 12n gives me 1 mod 5. Now, great. What I can do from these two, right? I can say that 3 to the power of 12n, when divided by 7, gives me remainder 1. And that same number, when divided by 5, gives me remainder 1. Well, that means that this same number, right, 3 to the power of 12n, will also give me remainder 1 when divided by their multiplication by 5 times 7, which is 35. So I will write over here that since 3 to the power of 12 and gives me 1 mod 7 and 1 mod 5, right? Then 3 to the power of 12n will also give me 1 mod 35 by their multiplication. And the same story for 2 to the power of 12n. Okay, it gives me 1 mod 7 and also gives me 1 mod 5. Well, then 2 to the power of 12n will also give me 1 mod 35, right? Great. Now what I need to do, I need to consider the difference, right? Since I have this expression, the difference of 3 to the power of 12n minus 2 to the power of 12n. So if I subtract them from each other, what I get is 3 to the power of 12n minus 2 to the power of 12n, right? If I subtract from this part, on this side, right, I will have the difference. And this will give me, on the right side, 1 minus 1 is 0, right? Mod 35. So basically, I have 0 mod 35. And what does it mean? Well, it means that remainder, right, is 0. If remainder, when this number is divided by 35, remainder is 0, then this number, right, is divisible by 35. And this is how you show it. Okay, let's move to the next one, Euler's function and Euler's theorem. Now you have the definition in your slides for Euler's function and for Euler's theorem as well. So basic meaning of Euler's function is the number of integer values that are relatively prime, okay, with this number inside, okay, which is, in this case, let's consider 1800. So, okay, now you have couple of properties and couple of theorems regarding Euler's function and how to find its value. Let's consider this problem. Find the value of phi, Euler's function, for 1800. Now what you need to consider is you need to factor out into prime factors, right? So we have this theorem which says that phi to the power of phi of p to the k, right? In this case p is prime and k is integer, is equal p times k minus 1, p to the power of k minus 1 multiplied by p minus 1. Okay? And we also have phi of m times n equal phi of m times phi of n if GCD of m and n equal to 1. So we can make use of these two theorems for our case, okay, to find this value. So first of all, I need to factor this into prime factors, right? So I can write this 1800 as 8 times 25 times 9, right? Well, I know that 8 is not a prime number, 25 either, and 9 either, right? So therefore, I can write 8 as a prime factor like this. 2 to the power of 3, right, times 25 is 5 to the power of 2, and 9 is 3 to the power of 2. Now 2, 5, and 3 are all prime numbers, right? And I can use this. But before that, I have the product of these numbers, right? So since I know that GCD, right, of 2 and 5, 2 and 3, right, GCD of 2 and 3 and GCD of 3 and 5 are all 1, right? I can make use of this theorem as well. That is, I can write them separately. Phi of 2 to the power of 3 times phi of 2 to the power 5 to the power of 2 multiplied by phi of 3 to the power of 2. Okay. Now after this, for each one of these functions, I can use this definition, right? So in my case, p will be 2 and k will be 3, right, for this first one. So that is 2 to the power of 3 minus 1 multiplied by 2 minus 1. Okay, so this is for the first. For the second one now, my p is 5 and k is 2, right? So 5 to the power of 2 minus 1 multiplied by 5 minus 1. And next one, my p is 3. So I will write 3 to the power of 2 minus 1 multiplied 3 minus 1. Now if I calculate this, right, what I have is over here 2 to the power of 2, which is 4, multiplied by 1. Over here I have 5 multiplied by 4. Over here I have 3 multiplied by 2. So if I calculate this one, I'm going to get 480. And that's it. This is how you calculate the value of phi, okay, of Euler's function. Now let's consider next problem, okay, now using Euler's theorem. So the definition of Euler's theorem is given in the slide. Please look it up, okay, and study and how it's used also. I'm going to discuss how we can actually apply it to solve this problem. So we need to show that n to the power of 12 gives me remainder 1 when divided by 72 if GCD of n and 72 is equal to 1. Okay, first of all, if I directly use Euler's theorem, right, that is, I can write it like this, okay? If use directly, then basically I will have n to the power of phi 72, right, should give me remainder 1 mod 72, right? And looks like it works out, right? Kind of easy problem. What we need to do is just calculate phi of 72 and that's it. So let's see. Phi of 72 is actually equal to what? 72 is 8 times 9, right? And 8 is 2 to the power of 3 and 9 is 3 to the power of 2, right? So basically I will have phi of 2 to the power of 3 multiplied phi of 3 to the power of 2. Now if I calculate, phi of 2 to the power of 3 is 4, right? From this we saw that 4, and phi of 3 to the power of 2 is 6, right? So 4 times 6 is 24. So basically what I have is n times n to the power of 24 gives me 1 when divided by 72. Okay, but I need power of 12, right? Well, some of you might think, well, maybe take square root. Well, the problem is that we cannot actually raise, okay, it to non-integer power. So we cannot raise it to non-integer power. So that is, we cannot do it like this, okay? No, okay? We cannot do it like this. We cannot raise it to non-integer power. So that's a problem, right? Then we have to approach this problem other way, because directly it's not working, right? So then let's see how we can approach this problem. So if you remember one of the previous problems when we used Fermat's theorem, we had divided, right, by 35, but 35 was not prime. So what we did is we considered 35 as factors of 5 and 7. So therefore, we can also consider 72 as, okay, 8 times 9, right? And then consider separately with 8 and with 9. So we're going to see actually how that works out. So we're going to do it like this. Instead, instead we're going to consider this as 8 and 9. And since I know that GCD of n and 72 is 1, then also GCD of n and 8 is 1, and GCD of n and 9 is also 1. So why do I need this? Well, I need this to satisfy the condition of Euler's theorem, right? Remember, by Euler's theorem, GCD of two of these numbers must be 1 if we want to use, right, Euler's theorem. So these conditions are satisfied. So let's go by the first. So that is GCD of n and 8 is equal to 1. Okay. Then let's say n to the power of phi of 8 gives me remainder 1 mod 8. Okay. So what I know about phi of 8, right? I can simply calculate phi of 8. Phi of 8 is simply 4, right? By this theorem. So basically I have n to the power of 4 gives me remainder 1 mod 8. Okay, now what I need is power of 12, right? So I don't have problem over here, right? I can raise it to integer power. So to get 12, I can simply raise it to the power of 3 and get n to the power of 12 gives me remainder 1 mod 8. Now let's consider the second one, right? So GCD of n and 9 is also 1. Then by Euler's theorem, right, n to the power of phi of 9 should give me 1 when divided by 9. And we remember that phi of 9 is equal to 6, right? So which means that this one is n to the power of 6 gives me 1 mod 9. Now what I need is power of 12. And in this case, again, simply I can raise it to the power of 2, right? No problem. 2 is integer and positive. So this will basically give me n to the power of 12 gives me remainder 1 mod 9. Now what I know is, again, that 8 and 9 are relatively prime, right? Their GCD is equal to 1. So that is GCD of 8 and 9 is equal to 1. And I also have that this number, n to the power of 12, when divided by 8 gives me remainder 1. And also when divided by 9 gives me remainder 1. So one and the same number when divided by two different numbers, which are relatively prime, right, gives me remainder 1. Then this same number, n to the power of 12, will also give me remainder 1 when divided by their product, that is mod 72. And this is the end, guys. This is how you prove it. I guess this was helpful and useful for you guys. If you have any questions, please feel free to come to me and ask for clarifications, and I'll give you more problems if you're interested in. Thank you all. This is it for today, and I'll see you in the next video.